Hi, I'm Jeffrey. So for my seminar course CH206, so I've been tasked with explaining the paper, improving the density of jammed disordered packings using ellipsoids. Okay, so in this paper that they have, you know, the researchers have some keen interest in finding which shapes it does fit better while having some disordered packings. So we shall look into what the researchers have been interested in, and there are some actually good results and some counterintuitive facts that we may not have been observed in our day-to-day life. Okay, and so proceeding with that, so let me try to ask you a few questions regarding that. So you are seeing here some three different shapes: spherical, prolate, and oblate. So of these three shapes, which shape do you think is the best fit while you are trying to pack it randomly? So you see the spherical particles arranged in some random manner, and the prolate particles and the oblate particles. Okay, so you know which of the shape may have the best packing. So we don't know about this right at this point, so we may say most of through our intuitive guess we may say it as a spherical particle, or as an outlier as a prolate or oblate. So let's say at the end of the presentation you may have some different ideas about which particles does have the best packing situation when they were jammed randomly or packed randomly. So yeah, before going to understand what these are, what these terms which in my presentation is going to mean to you, so let's understand some key concepts in there. So I hope you may all know about packing density. So it's the number of particles, how much amount of particle that you can closely packed in a good manner in some confined space. Okay, so it's nothing but the total amount of particles which is taking the space on some finite amount of space. And then the coordination number. The coordination number is nothing but how much particles are being surrounded by a single particle. And then jamming. So these are some kind of phenomena that you can really observe in some solid handling. So if the shape of the like let's say some solid is being downpoured in some kind of this kind of vertical thing, and then it may will be forming an arch shape which will be jamming the entire flow movement of those solid particles, and that's known as jamming. And then there is caging. So caging, in the sense, the nearby particles will be making the actual central particle not to move, not to freely move from some of its mean point, and that we call it as caging. And let's get to know some geometrical interpretation which may be useful in this presentation. And yeah, here is the aspect ratio. So aspect ratio, so in this paper the authors were specifically interested in dealing with some kind of spheroid and ellipsoid particles. Okay, so ellipsoid are the general type. So you can say that, so for ellipsoid we can define it by three terms. Those are A, B and C. So for the A, B, those were defined in terms of some minor and major axis as like 2D ellipses, but for 3D ellipse there will be another third axis that we can call C. So for general ellipse, so these will be the defining factors of their shape. But for spheroids are literally those ellipses, but in one point of perspective these are looks like some cross-sectional circles. Okay, so we just really need some only two axes to specifically define that. So for a spheroid, the aspect ratio is given as the length of the unique polar axis to the length of an equatorial axis. So in very short, for an oblate the aspect ratio is less than 1, and for a prolate the aspect ratio is greater than 1, which may look like a grain of sand and the latter looks like a disc, but when the aspect ratio is equals to 1 it looks like a sphere. Okay. So let's see, where the authors were trying to do something simple, and the approach was so nice. So in here what they were trying to do is they just want to find the maximum packing or the best possible packing in some jammed random packing, right? So what the others tried is like, okay, let's try to do some simulation first. Okay, so the simulation says like, so there is a box, as you can see in the photo figure I have given you. There's a box and there are some random particles. Okay, so the others were interested in simulate the random packings here. So for that they use some algorithm to simulate all those random packing kind of movement. What they did is like they started every of those particles at some small point particles, and then they try to inflate them with the vibrations. So as the particle grows in size, so and also they do have vibration, so they will be settling in some most favorable or less entropical arrangement. Okay, so that's how the simulation works. And then the authors, using the simulation post processing, they took the results with cross sectioning and finding the number of coordinations and many other the data that they need. And then the authors were trying to do the simulation as a reality experiment. Now you can see how simple and how nice these experiments are. The authors were using the MLM candies, which were actually in a 5 liter of round this spherical bowl, and they tried to jiggle it up and then they tried to settle it. Okay? The settle is nothing. They tried to shake it well much, and then the fixed packing is what we really need. And in that candy experiment, so what they did is, after the every candy particles been settled up, they used the MRI to scan in several axes, and they took the data which that will be necessary for us, as similar like in the simulation part. And then let's go into some inferences. The inferences looks very good. Okay, so in here, this is the plot between the volume fraction and the aspect ratio. Okay, so in here the aspect ratio and the aspect ratio for the prolate, oblate, and the general ellipsoids are given with respect to the volume fraction. You can see that at the aspect ratio is equals to 1, there is a dip in the volume fraction. We already know the aspect ratio for 1 is a sphere. So for a sphere, while you are trying to pack it randomly, the volume fraction is the least. But if you try to change the aspect ratio smaller, then you can see that the volume fraction is spiking up. Okay, even for small changes in the aspect ratio. So which says that the sphere is not the most optimum packing for the random packing. Oh well, this actually contradicts our intuition, and it literally says that if you just add some irregularities to some very regular sphere, then that may increase your volume fraction. Okay, so this is some kind of an eye opener, and you can see these graphs literally shows you everything. If you try to increase the asphericity, okay, or the non-sphericalness of the particle, then the volume fraction is increasing. But also there comes with the expense. So as you increase the as you increase the aspect ratio, then it's showing some kind of a maxima and a maxima kind of thing at the right side and also left side. Okay, and also the one I have shown in the red mark is the one that we have plotted, or done the experimental one, so which has some errors, and we can actually see the experimental one and the simulation ones are kind of closely matching it with each other. Okay, and well, you can ask the question, why as we are increasing the aspect ratio, the volume fraction is actually decreasing after some certain point? Well, it has to do with a lot with the shape irregularness thing. Well, I think you can understand it with the next slides. Let's go forward. So why the things happen? So those are happening because of the rotation and the exclusion, excluded volumes. So the aspect ratio at the far right and the far left are having some kind of weird shapes, right? So at the far left, okay, so those are oblates. So you will be having something like a coin shaped objects. As you go on the aspect ratio on the right side, you will be having some needle kind of thing. Okay, so I am having here some better analogy of that. So if you try to fit a coin and some needle kind of thing, and you try to shake it up and then it settles, and if you try to calculate the volume fraction, then you got to know that the volume fraction that you will be calculating will be far less for this exotic shapes. Okay, so that's the same thing that's happened. So that we are trying to explain it using the authors were trying to explain it using the rotation and excluded volume. Okay, and then you can see there's the another proof like counting the contacts. Okay, so they took the cross-sectional views and then they were counting the number of coordinations that each of the particles does have. And while looking onto that, you can see, unlike the volume fraction graph, in here we are getting something kind of weird. In here we are having a minima as the sphere, that is the sphere has the least coordination number. And as we trying to slightly move the aspect ratio, the coordination number is increasing and it remains constant for wide range of aspect ratio at the far left and far right. And this looks good, and this is one of the thing which is about to tell us caging. So as we are having some different weird shapes, so those weird shapes will be trying to cage the particle in some particular position, but even though those were having some kind of different shapes. And also this number of contact points also tells about the stability or the adherences of the particle with one another. Okay, and so with the conclusion, we can see these are some of the interesting points that we do notice. We need not want to in here about the why sphere is the very least optimal thing and why a small deviation in the shapes are giving us much more interesting or high efficient volume fraction. These explanations are need not want to be some kind of complex thing, which all these things can be explained by some easy intuitive concepts. Okay, so yeah, so the authors have done a very clever way to explain all these things using the MLM candies to the MRI machines. So the real world impact, one may ask like, oh yeah, well, okay, they have done some good experiment and it I've taken my brain by storm, but what's the real use of it in the world? Okay, so sometimes arranging the particles will be too much time consuming, and that may take some real machinery to do that. But if the particle size were too less, arranging them in an ordered way, it will be making a lot of hard time for us. Okay, but unless if we could just make some right shape, then through natural settling, then it can find the best optimum shape, right? So yeah, so it does have a major applications in ceramic powder metallurgies. Okay, so using this ellipsoidal or small deviations from the sphericity of being perfect sphere, a small deviation can induce a lot of volume fraction, and that can improve the density of the material. So if you want to try to increase the density of the material, then yeah, the slight inclusion in the non-spherical nature can do that. And the others have proved that, and yeah, here is the reference that I used to present this topic, and thank you.